Okay, so yeah, so thank you for being here, as Nana was saying. And so yeah, we'll actually, this is not really directly related to algebraic statistics, but it is to computing in geometry. And there is a connection that I will highlight. So yeah, so convex halls of curves. So let me just go into it. And the motivating question is, we have a path. And so a path, you can think of it as some continuous function that goes from 0, 1 to Rd, right? So it's some curve that lives in Rd. And we think of this, in this curve, this map is a curve, this I call it X. And we're going to look at the convex hull of this curve, right? So maybe it looks something like that. And so you can think of the curve, and then you take the convex hull, right? So then one of the motivating questions here is, well, what is the volume of this convex hull? And we're looking for nice curves for which we can actually write some kind of formula, some closed form expression of what is this volume. And so, well, one class of nice curves would be given by this totally positive torsion curves, and these are we found actually quite recently. Like, so this definition is from this paper last year, 2022, by Jaume de Dios Pont and collaborators. And well, they say a path has totally positive torsion if this matrix that you form by taking all the derivatives, higher order derivatives, or to order d, then you have this d by d matrix. And then if all the principal minors, leading principal minors, are positive, right? So this is a positive definite matrix, then they call this totally positive torsion. Okay? And well, one of the things they prove in this paper is precisely some closed form formulas for the volume of the convex hull of such a curve. And you can see the form that they take. So there are some integrals, and there are some determinants of matrices that also have to do with the derivatives of the path and displacements. You can see like how far it moves. And these are the variables t's that, and you're integrating with some simplex here that has this particular form. And then, well, there is a slightly different, you need to think of the even case and the odd case a bit differently. But okay, so what we want to do is like try to understand, connect these formulas and actually extend them to not only this totally positive torsion, which we think it's a bit restrictive. In particular, this has to be differentiable, has to be many times differentiable, right, to have this property. So what we're going to do is look at signatures. So path signatures, and what is this? Well, consider a multi-index. So I1 to ik. Each one of these is a number from 1 to d. And so what you're going to do is you do this kind of integral, and then you take the product of the derivatives, and the coordinates are going to be read off directly from this I. And this is the path signature of x with respect to I. And if you vary I over all the possible d to the k possibilities, right? So you're going to get d to the k entries. This is a tensor of order k. So it's going to be an array that's of the form d by d by d by d, k times. And so this is the notation I'm using, sigma kx, and it lives in rd to the k. And so this is the so-called path signature. And I think this was already mentioned yesterday in the plenary by Ortega. And so here, signatures, so they have this explicit form in terms of iterated integrals. And so just to have an example, to see maybe this is a bit scary at first, when k equals 1, this is just the fundamental theorem of calculus. Because you only have one thing, so this is just xi prime That would be the entry sigma I. And then you can see this just tells you xi of 1 minus xi of 0. So this is how much the path moved in this direction I, right? So from 0 to 1, what was the total displacement? So that's what this first signature is telling you. And so that's exactly what I write here. x1 minus x0, it's a vector, right? In RD, it's a vector. And then this is the first signature. And so just I want to mention a little bit of the history. So the historical remark is that these were introduced by Chen in the 50s. And he was thinking of things like geometric invariance and generalized Baker-Hausdorff formula. And well, the signature then for him is just a sequence of all the tensors that you get at every level. So you start doing iterated integrals with more and more iterants. So this would be to n and goes to infinity. And the very nice thing that has been proven is that the signature determines the paths up to small things. And so that means that if you know the signature, complete signature of a path, you can basically recover it. So this is a very nice property. And so this is Terry Lyons, for example, at Oxford. And they have been used in stochastic analysis, in particular for rough paths. So there is the one reference, Peter Fritz, Martin Herrer. So they're very useful, and also for data. So machine learning, so I have this reference here. So because, well, if you have a path, like you have some time series, for example, that's your data, then you can encode this path using the signature as a feature. That's what you can do. A neural network, for example, by looking at the different signatures at every level. Okay, so that was just it. So now what I'm going to introduce is the alternating signature, which is the same idea, but now, so you're going to take the signatures and you're going to take a sum of them by permuting the indices, and then you permute them according to their sign. And then you just normalize by k factorial, and you do this over all the possible permutations. Okay, so then you just do a sum, this alternating sum of the signatures, and we call this alpha I, and this would be the level k alternating signature when you look at alpha. So this is alpha k, and this will be an alternating tensor. And well, the first signature is equal to the alternating. If I just choose the k equals 1, then I just have the usual thing. But k equals 2, it's already has a very nice geometric meaning as well. This will be 1/2 of sigma ij minus sigma ji, and this is the so-called Levy area. Let me show you a picture. So what is the Levy area? So suppose the path is this red curve. So the blue would be the total displacement, right? And so now there is an area that's enclosed here, right, above the curve and below the curve. So if you consider this area with a plus sign and this with a minus sign, and then you add them up, you're going to get precisely this number, 1/2 of sigma 1, 2 minus sigma 2, 1. So that means that you can recover this geometric information of this area from this number. And so this is the alternating signature for k equals 2. And in general, this is going to be what one gets. So basically, so here Joshua Deal and Jeremy Rasenstein observed that for the moment curve, a very nice curve, very important, right? Also called the rational normal curve. This one, it's true that the volume of the convex hull is given by this alternating signature. And in that particular case where k equals d, well, that's the connection, right? So you can write this alternating signature in terms of a determinant of these derivatives, and that's how you get back these formulas that we were seeing at the beginning. And they say, but this was only for the moment curve, and they say, well, in general, this should hold for some curves that satisfy some kind of monotonicity, and that's what we wanted to try to understand. What kind of nice curves can we consider? And we looked at this very nice family, that's the d-order curves. They're actually known by many different names. I'm going to list some of them. But so a path is going to be d-order if you take any hyperplane right? Then this intersects the path in at most d points. Okay, so the example I had here, it's not the order, because you can see this intersects in at least 3 points, this line, right? So this one would not be to order, but this one is, the moment curve is. And I said there are many names. This is also known as comonotone, strictly comonotone, convex, strictly convex, hyperconvex. There are, and all refer to this, and these are some authors that have used these curves. And so the order we took from Bernd. And well, one of the nice properties that connects to discrete geometry is that if you take a convex hull of points in such a curve, you're going to get a so-called cyclic polytope. So if you like discrete geometry, if you like polytopes, that's a nice connection. Okay, so we actually extend this a little bit more, and we talk about cyclic curves, and cyclic is just the uniform limit of the order curves. So you just take limit of the order curves, and then we call this cyclic. And we actually have then this kind of strict inclusion. So cyclic is like the most general. And this is an example of a curve that has some line segments here that are straight and then curved. So this would be an example of a cyclic curve that's not the order and it's not totally positive torsion, right? Because like here, so you can think of the order is already nice because this is a global condition, while totally positive torsion is very local, right? You need to look at the point and look at all the derivatives at a point. And well, maybe the derivatives don't even exist, right? So this is very general. And well, so what's the punchline? The punchline is the main theorem is that this nice equality, that the volume of the convex hull is given by this alternating signature, holds for all cyclic curves. So that's our main theorem. And for d equals 3, it looks like this. Again, so just take all the permutations and look at the sign, and yeah, this 1 over k factorial. And a nice corollary, so I don't have time to tell you precisely what it is, but a nice corollary of this interpretation in terms of signature is that the volume can be actually written as some displacement times signed areas. So these kind of Levy areas that we had in 2 dimension. So this is always true for any dimension. So that's one of the nice things that come from the signatures. And so let me finish with the exploring, well, what about the converse, right? So if I know this is true, is this necessarily cyclic? Well, that's not true. This is a counterexample of this is a path that goes like this. There is a small loop and then there is a bigger loop. And so this one, if you take the convex hull, you're gonna get this rectangle. And then the volume is exactly gonna be the sum of this plus this area. So this is true, but this is not cyclic. You can see that this is not a cyclic curve. So this is not the most general that we can have, but we conjecture that a curve will be cyclic if and only if the formula holds for every subpath that you can take. And then, so we believe this would be true, and there would be another characterization of cyclic. Okay, so and last open question would be, well, if you have a general curve, what does this mean geometrically, right? So what kind of signed volume is going on in higher dimensions? And so I leave you with some references, and thank you for your attention.
Are there any questions for Carlos? There's plenty of time for questions. So. Maybe I have one question. So are there other families of curves other than cyclic curves that satisfy the formula for the signature?
Well, that is the question. So this is the largest family that we found somehow.
So that's the conjecture.
And so, yeah, this would kind of resolve the idea. Okay, like this is like the largest one for which this would hold for all subpaths. And yeah, so we believe this is somehow the right family. Yeah.
Thank you. Any other questions or comments?
So what is the time complexity the naive approach, but can you beat the naive approach?
To compute the volume, you mean?
Yeah.
Well, we're not computing in this case. I mean, okay, one can. It would be how do you actually compute this? And this is a good question. So one can do it. I guess the naive approach. One could try to do some kind of Monte Carlo spacing. But here, if you want to do the integrals, one also uses numerical integration. So I guess it would depend on how good you are at estimating these integrals.
But also in computational geometry, we know that if you sample on the moment curve, you got maximal complexity combinatorial polytopes for the convex, right?
Right. So I mean so the cyclic polytopes that are coming from the rational number curve are had the highest complexity in terms of facets and faces and
exactly. So you could discretize and make and look at some kind of law of large numbers and you
Oh yeah, that's something that we could look at. Yeah, thanks.
Any other questions or comments? Okay, then thank you very much. Let's thank
Thank you.
Carlos again.